Now, in this class, Crystal Structure Part 4, I am going to discuss about the reciprocal lattice. Now, before we start with the reciprocal lattice, previously in my previous class, I have considered that the crystal is made up of basically lattice points, and for simplification I have to assume that these lattice points basically are placed on some set of planes, and we can assume only those set of planes are responsible for generation of whole crystal structure, and those planes are designated by Miller indices. Now I have mentioned another thing, that why Miller indices comes, and what are the factors that how can you determine the Miller indices of a particular plane. Now, so before start with the concept of reciprocal lattice, we have to consider that the diffraction of X-ray by a crystal may be thought as a reflection by a set of parallel planes that constitutes a crystal. As I considered that crystal is made up of set of planes, so those planes are basically responsible for X-ray diffraction. Now, why X-ray? Why not the visible light which we are used? Because of the dimension of that particular crystal, which must be comparable with the wavelength of X-ray, or shorter wavelength than that of an X-ray. Now, we know that when these planes of are considered, then for a particular HKL we can designate a particular set of planes. So I mention 4 points here why reciprocal lattice is important. First of all, the crystal lattice that can be considered as a set of parallel planes, and we forget about the effect of any particular lattice point, though that those planes are made up of at least 3 non-coplanar lattice points. But we can forget, for our simplification, about the lattice point when we consider the exposure of that particular crystal under electromagnetic radiation, mainly light. Here we can use X-ray. So just the concept of planes basically are rather simplification of crystal structure from three-dimensional lattice points to a two-dimensional plane. Now we can use the proper wavelength of light to visualize or to interact with the crystal. So why we need to interact? If we want to know the internal structure of a crystalline material, we have to interact through with the crystal, and that interaction basically made up of by exposure of that crystal under certain electromagnetic radiation. Now, crystal is a microscopic object. Microscopic object means its dimension is of the order of Armstrong. Okay, its spacing, lattice spacing I can say rather. So as that have a dimension of Armstrong, So normal visible light which have more higher wavelength than that of the dimension of X-ray does not uh, serve our purpose. So we have to think of another alternative electromagnetic radiation whose wavelength might be comparable with that of dimension of crystal. So keeping in mind that we have to choose a certain wavelength, we can use the X-ray or neutron diffraction or synchrotron radiation to get our desired result. So X-ray definitely, if we use the monochromatic X radiation, X-ray have wavelength approximately 1 to 2 Armstrong nearly. So that particular wavelength is comparable with the dimension of the spacing between crystal planes, or I can say the lattice spacing. So previously we see that a definite set of plane can be designated by a definite Miller indices, and the definite set of plane, as they are designated by definite Miller indices, they must have a definite interplanar spacing. So we have to choose such an X-ray whose wavelength will be comparable to the dimension of that specific spacing between adjacent planes. But the problem is that we cannot designate Miller indices of for a particular crystal uniquely. Why? As we can see here, from the very first sense of crystal geometry, we can say that crystal is basically made up of lattice and basis. And if that crystal is made up of lattice and basis, that crystal have a definite geometry. And depending on the geometry or the crystal lattice arrangement, we can visualize that particular crystal in terms of unit cell and in terms of interplanar spacing or in terms of lattice parameters ABC. Now the concept of unit cell is basically the smallest entity within the crystal in which all types of property are preserved. But when you are trying to visualize the fact about the crystal, you need to assume that there must be some parallel set of planes by which the crystal is made of, and we can forget those lattice points. But as the choice of unit cell is not unique, so the choice of planes are not also unique. And in this case, I have to say that we consider separate slope for a particular crystal. Okay, we can choose several slope of several planes of different slopes for a particular crystal, and when we consider different planes of different slopes, then the particular interaction of that crystal with radiation becomes differently designated. So we need a more simple approach to visualize the surface of different planes, and of course in this case several difficulties can arise. Now what are the difficulties that can arise? I come into this picture. So let us consider that in this particular picture you can see here, this is the origin, and with respect to this origin I can have a different lattice points, and I can use the specific depending on the direction I can choose the specific lattice points as 1 0 0, 2 0 0, 3 0 0. Okay, and of course this point is 1 1 0, and so on, 2 1 0, 3 1 0, etc. So in this way I designate different lattice points, and the plane that are passing through 1 0 0 is defined by this black line. So 1 0 0 planes are those parallel set of planes. I am just putting my mouse pointer here and show that how could you draw 1 0 0 plane, these parallel planes. Okay, so these parallel planes are basically 1 0 0 planes. Now what about 1 2 0 plane? So 1 2 0 plane is defined by this green line. So this green line is 1 2 0. Now you draw a plane 1 2 0, 1 2 0 with a definite direction, this D120. So this vector is the direct lattice spacing spacing of the plane between or the spacing between two lattice point. Okay, so these are the spacing between two planes designated by the Miller indices 1 to 0, and this is the spacing between two planes which is designated by the Miller indices 1 1 0. Now 1 3 0 is defined by this brown line, and its lattice plane spacing is basically defined by this brown line. Now you can see here, if any particular radiation that are going to incident on a crystal, one can choose any of these planes for the calculation or for getting the geometry of that crystal. But one thing is correct, that if you particularly choose a set of planes, that means either it is 1 1 0 or it is 1 2 0, then those planes have got a definite geometry. Until and unless you are going to choose a definite set of planes, say for example, if I am going to choose 1 1 0 plane, so 1 1 0 plane have some definite geometry, definite spacing, definite interval they are placed. For 1 2 0, same sequence is going to happen. So these planes have a definite geometry, although its two-dimensional visualization is very difficult. But at the same time, a particular thing is associated with these planes, that if you draw a normal on the plane, so let us consider this 1 1 0 plane. Okay, this is 1 1 0 plane. Now if there exist parallel planes of 1 1 0, and if you draw a normal, this normal have got a definite direction. So the normal can give a proper representation of a set of parallel planes if the interplanar, the information of interplanar spacing will be introduced in that particular normal. Mind it. So you have to give a definite set of planes, and you are choosing the normals on that particular set of planes, and you are going to introduce the information of interplanar spacing in that particular normal, that can provide a very better understanding of this crystal diffraction. So as you see here in this picture, that the normals of 110 is this, the normals of 120 is this, and normals of 130 is this, has definite direction. So if you replace that planes with this normals, it can serve the, or it can preserve the geometry of this whole crystal. But where lies the problem? What about the intermolecular spacing, interplanar spacing? So this line is very, very important, that if one can introduce the interplanar spacing information in these normals, it may fulfill the expected requirements of visualization of planes. So you need not try to visualize a two-dimensional plane. Rather, you are going to replace those two-dimensional set of planes by some normals. Okay, and I am very intelligently, I can say, introduce the information of interplanar spacing in that particular normal. Now, but how could you introduce that concept? But how? So here lies the construction of reciprocal lattice. So how could you construct? Say for example, these brown lines are the set of parallel planes. They are two-dimensional, and as I am going to see along the parallel of its plane, so it looks like a line. Ultimately, these are the two-dimensional planes in a crystal system, and this point I choose an origin, and through this origin I am drawing a normal which is perpendicular to this set of parallel planes, right? Now what are the characteristics of those system? So first key, I choose a set of planes, I draw a normal, and I put some points on the normal which is basically having the dimension just inverse to that of interplanar spacing, right? So my purpose of introduction of information as well as orientation of that plane is fulfilled, right? So the information about the interplanar spacing is introduced within that normal, and the direction, that is orientation of that plane, is defined by that normal itself. Okay, so the construction is basically normal on the set of planes from a common origin, and the length of normal being proportional to that of reciprocal of interplanar spacing of the corresponding set of planes. And then the endpoints of normals form a lattice which is called the reciprocal lattice, right? So if the dimension of this black normal is 1 upon d100, and this point and this point having this dimension, then now if I distribute the whole points on this normal, it can serve my purpose of replacement of this plane by normal. So once I replace that particular normal by its interplanar spacing, I may forget about those planes. Okay. Now those points have definitely some characteristics. Each point in the reciprocal lattice, that means each point which I defined on this normal, having a dimension just inverse to that of interplanar spacing, that preserve the characteristics of particular set of planes which it represent. The second point is that the direction with respect to origin that represent the orientation of that plane, and the distance from the origin, this distance from this origin represent reciprocal of the interplanar spacing. So information about the interplanar spacing, right? So these are the characteristics of reciprocal lattice. Now how could you construct the reciprocal lattice? Choose any arbitrary set of planes and any lattice point as a common origin of construction of a reciprocal lattice. Now keep that point fixed. Keep that particular point which you are choosing to generate this reciprocal lattice fixed throughout the construction. From that origin, draw a normal to each planes having same HKL. So there are lots and infinite number of planes within the crystal, and obviously there are infinite number of choice of that set of planes. From that infinite number of choice of that set of plane, you have to choose those planes having same HKL. Okay. Now once you choose that particular set of HKL, you are going to draw a normal on that particular planes having same HKL. Now what in the next part, what are you doing? You are going to choose a point on that normal for each HKL having the distance from the origin just inverse to that of direct lattice space. So if there exist, I mean to say, for assume there are 5 planes and you are choosing a normal on that 5 parallel planes, and according to the general procedure of construction of reciprocal lattice, you are putting some points on that particular normal, keeping in mind that those points must have a separation proportional to inverse of direct lattice spacing. Now if you have 5 set of planes, 5 number of planes, you must have 5 number of points in on that normal, right? So if there exist infinite number of planes, so there will be infinite number of lattice points. Okay, and of course if you choose that normal, there will be infinite number of points. But here exists a concept that when you were getting the information about the crystal, which when you were trying to get the information about the crystal and you expose that particular crystal under uh, the electromagnetic radiation, you are not yet get infinite number of reflections, but you are getting some finite number of reflections. So here lies a fallacy that why we are not getting infinite number of information, infinite number of reflection, though the crystal is made up of infinite number of planes. So when I am going to give detail about the Bragg's law, then I am definitely going to discuss about this topic. But till now we can say that the number of set of planes in the direct space must be equivalent to the number of lattice point in the reciprocal space, right? And what you are going to do, you are going to distribute that particular point. Once you choose the spacing between 2 points by distance 1 by dh scale, now distribute the set of points on that particular normal having equal separation and repeat this for 3-dimensional set of planes. You will get the whole crystal structure in reciprocal space, and that will definitely says about the reciprocal lattice. So reciprocal lattice is basically just a reverse replica of direct space lattice, but somehow I can say that the reciprocal lattice may be or may not be identical with that of direct lattice, right? Okay, now these are, at the left hand side you can see it is a unit cell of a definite crystal. This cell, as you see here, this is a monoclinic cell, and as this is a monoclinic cell, definitely when we are going to choose A, B, C, this 3 axis, this is B, this is C, and this is obviously A. So these 3 axes represent the direct space axis. When we are choosing the direct space lattice, we are going to choose these 3 axes for to represent that crystal. But in reciprocal lattice, those planes are replaced by their normals, and obviously the direction of that normal must coincide with the choice of axis. So if you choose this as C star, this as A star, and this as B star, these 3 axes represent the reciprocal lattice. So in this case, the direct lattice must not same as that of reciprocal lattice. Okay. Now if you choose the direct lattice, And you come to this picture. This is the picture of a reciprocal lattice. Now this is the origin, and choose some points on this three perpendicular. So as you see here, this face and this face are parallel to each other, but they are inclined at some angle with this horizontal plane. Okay, so this plane, that is the plane of BDFG, that are inclined at certain angle with this plane OADB. So as these planes are inclined, now if you draw the perpendicular from this origin on this particular plane, the direction of perpendicular is along this line B star. So I can choose this axis B star here. This is the B star axis. Okay. Now this is the A axis, and as you can see here, as this is monoclinic cell, so two angles will be pi by 2 and one will be not equal to pi by 2, and this axis, this will be perpendicular to the parallel set of planes. Now if instead of monoclinic, if this will be triclinic, what is going to happen? If this is triclinic, then there will be no symmetry. So there are alpha, beta, gamma angles which are not equal to 90 degree. So you can get three mutually perpendicular axes instead of three inclined axes, right? So these three axes A, B, C serve basically that purpose. That represent the direction of perpendicular on set of planes, right? Now choose these points in reciprocal space. And what are the spacing between any two points along this C star direction? That will be equal to 1 by C. And you choose the lattice spacing between these 2 points along A, that is 1 by A, and lattice spacing along this is 1 by B. Now this structure definitely serve the purpose of reciprocal lattice, or this represents the reciprocal lattice of this direct lattice, right? Now what happens if the dimension of direct lattice is small, of the order of Armstrong? So the dimension in reciprocal lattice will be much greater, because it is just the inverse of direct space lattice. So how much short the direct lattice be, that much longer becomes its reciprocal lattice. And I give you some formula about how could you construct three reciprocal lattice, three reciprocal vectors, rather I can say three set of vectors, once some vectors A, B, C are given for a system. Now what are this A, B, C and A star, B star, C star? So come to the part of vector calculation, vector analysis. So in vector analysis, you can see that any particular three vectors, if it is given in terms of A, B, C, and these three vectors represent the basis of any set of vectors, then any particular vector can be generated by using some coefficient with that set of vectors. Now any vectors A can be generated as ax I cap, ay j cap, az k cap in three-dimensional space, and you can expand that particular vector in terms of three basis vector ijk. In crystal space, in direct space, as you see here in this direct space, the smallest number of translation along C will be represented by this C vector. The smallest amount of translation along B axis will be represented by this B, and the smallest number of translation along A axis is represented by A. So A, B, C in here, A, B, C is nothing but it represent the same thing as in case of vector I, J, K represent. So they are basically the basis of forming any direct crystal. On the other hand, this A star, B star and C star, they are the basis vector in reciprocal space. So by that particular set of three vectors A star, B star, C star, one can move from any point in this reciprocal lattice to other point. In direct space, that particular translation is given by ABC basis vector. So if you can choose any vector that are having say for example H A vector plus K B vector plus L C vector, that is basically represent the translation of some planes having Miller indices HKL. And in the same way, in reciprocal lattice, that are given by A star, B star, C star, right? So this is basically the construction of reciprocal lattice in three-dimensional space. Now what happens here? So from reciprocal basis vector, now I have to consider a reciprocal lattice vector. Now what are the reciprocal lattice vector? In direct space, you can choose any three non-coplanar vector ABC which can define a unit cell in the crystal system. Now as you see in this figure, this A, B, C, that are basically three basis vector of an unit cell in a direct space of a lattice, of a crystal lattice. Now we are going to define a vector A star which is perpendicular to a plane which contains a vector A, okay, or which contains a plane having just contains B and C vector. And I am definitely drawing the perpendicular on the plane which contains vector B and C, and that is represented by A star. Now for a normal crystal, you see that A dot B and B dot C will be associated with some definite relation by their interplanar axial angles. But in this case, from my point of choice, as I choose that perpendicular on the set of planes having containing B and C vector, so one must define this A star vector in such a way that A star dot A will be 1, just a number, it is not a vector, this is unit 1. A star dot B equal to A star dot C, both of them are 0. So one can say that this A star vector is a kind of vector which is perpendicular to B and C. And obviously when we are going to make a dot product with A star dot A, this definitely gives me 1. So as I from the point of dimension, I can say that A star is just inverse of dimension of A, right? I can't say anything about the direction of A between A star and A. I just say that the direction of A star with B and C is perpendicular. And I am just drawing here that you see here, this is perpendicular, this is perpendicular. But I can't say anything about the angle between A star and A. Now the vector A star that is perpendicular to both B and C vector. And now if you define two other vectors that are basically B star and C star, that similarly defines that thing. Now in the previous picture, if you see here, so the unit cell basically that are defined by A, B, C, and the vector which is defined by me, when I am going to replace the concept of plane by its normal, then it is defined by just A star. So, and in the second part, I can see here, since the scalar product between A star with both B and C is 0, then it must be perpendicular to each of them, and hence perpendicular to the plane that are defined by these two vectors B and C, right? Now this fixed direction A star and its angular relation with A is defined by A star equal to 1. Now the magnitude of A and A star is interrelated by that particular relation A star equal to 1. Okay, so A star is a definite type of vector which can represent both about the direction of the set of planes that are contains B and C vector, and at the same times from A dot A star equal to 1, I can assume about the dimension of A star vector. Mind it. So the second two relation, this is B dot C in the previous picture, A star dot B and A star dot C equal to 0. This tells about the orientation of the plane, and this A star A equal to 1, this gives me the information about the spacing between any 2 points that is defined on this A star axis by myself according to construction, right? Okay, so in the same way I can define two other vectors B star and C star in such a way that are defined by A dot B star equal to B star dot C equal to 0 and B dot B star equal to 1. In the next part, for sister vector, A dot sister equal to B dot sister equal to 0, as you see here, and C dot sister equal to 1. Now if you see here, just as three vectors ABC define a space lattice in direct space, three vector A star B star sister that define another lattice which is given by the name reciprocal lattice. So in direct space, the lattice are defined by ABC vector, and when you translate from one point to another point, you need three basis vector as ABC with proper choice of integers. Just multiply them with ABC and add them, you can get a vector by which you can translate from one point to another point in direct space. In the similar way, you can choose three vector A star B star sister in reciprocal lattice, and you use the same concept, the same thing, the different constants. Just multiply with three vectors and add them. You definitely can go from one point to another point in reciprocal lattice. So direct lattice and reciprocal lattice having the same approach about the geometry of the crystal. Okay, now the reciprocal nature of this lattice as compared to real lattice is suggested by this non-zero diagonal coefficient. Okay, and we shall see that the reciprocal relationship will also show itself in other way. So it is possible to define a point of reciprocal lattice by three integers that are giving the displacement from origin in terms of smallest unit by A star, B star and C star. So such reciprocal lattice point can be denoted by the vector H A star, K B star, L C star, where H, K, L are three integers. They are the basically mirror indices in the set of planes as you see here, right? So what you see, what I'm just talking in my previous part, that just like three non-coplanar vector ABC in direct space, or that ABC is defined unit cell in real space, you choose three non-coplanar vector A star, B star, C star in another lattice that also defined the unit cell in reciprocal space, that are called the reciprocal lattice. And if you choose three integers H, K, L, you just multiply with A star, B star, C star and add them. This quantity sigma HKL, this represent the reciprocal lattice vector. Okay, and this reciprocal lattice vector have a definite very good concept when we are going to discuss the Laue treatment of crystal diffraction. Okay, that reciprocal lattice have definite information about that particular thing. Now these are some points about the reciprocal lattice. So as there exists an infinite number of possible choices of unit cell in direct lattice, The same thing happens in case of reciprocal lattice. So the choice of reciprocal lattice is not unique, right? But what are the fact about the reciprocal lattice? The three non-coplanar vector A star, B star, C star, by which we are going to define a reciprocal lattice, that must depend on the initial choice of direct space lattice in terms of ABC. So once you primarily choose a set of ABC to define a unit cell, then you get a unique A star, B star, C star. So for unique ABC, you get unique X star, B star, C star. Now either this A star, B star, C star depends on ABC. In the reverse way, I can say that ABC depends on A star, B star, C star. So primarily, when we are choosing some planes or some unit cells, we have to keep in mind that the concept of reciprocal lattice depend on that ABC which I am primarily choosing for my experiment. Okay, and the next part is that for a particular direct space lattice, the corresponding reciprocal lattice must be unique. I mentioned earlier. So once you get the information about that reciprocal lattice ABC, now a unit cell of a crystal in direct space that can be defined by unit cell edge vector ABC and obviously interaxial angles alpha, beta, gamma. In a similar way, the unit cell in reciprocal lattice space, which is defined by myself depending on a particular choice of ABC, can be found by reciprocal cell edges vector A star, B star, C star. I'm sorry about these things because this A star, B star, C star will be bold because they are the vectors, and obviously reciprocal interaxial angles alpha star, beta star, gamma star. Mind it, this A star, B star and C star, they are the vectors, not the scalars. Though they must be bold. There is typographical mistake here. So this is the interaxial angles alpha, beta and gamma. Now once you choose a definite set of ABC, so a unit cell of a crystal can be defined by ABC and alpha, beta, gamma. So first let us choose a definite unit cell having cell edges A, B and C vectors. Now if you go for a triple product among these three vectors by A dot B cross C, this A dot B cross C is nothing but the volume of parallelopiped. So from this point of view, you can see that once I am going to choose a unit cell, my choice of unit cell will be a parallelopiped in 3 dimension. So the volume element of a unit cell is A dot B cross C or B dot C cross A or C dot A cross B. They are the same as the triple product. If you're going to interchange these three, they gives me the same result. So this volume of the parallelogram parallelopiped is basically A dot B cross C. Now if you just expand that vectors in terms of 3 basis vector ijk, you will definitely see here that this ijk, they are the orthogonal basis vector, and in terms of this orthogonal basis vector I am going to define this 3 non-coplanar vector ABC, right? So you are going to reduce or expand ABC in terms of ax, ay, az by ax I cap plus ay j cap plus az k cap. Same thing happens for two vectors b and c. B is defined by bx I cap, by j cap and bz k cap, and c equal to cx I cap, cy j cap plus cz k cap. Now what is the volume element? It is just the determinant bit of this ax, ay, az, bx, by, bz and cx, cy, cz. They are elements of that determinant as you get from a triple product according to the vector. Now if you choose v square, you just multiply this determinant with another determinant, and what you will get ultimately, this gives me, if you expand and simplify the whole thing, you will get that this v square will be just the dot product between a dot b, a dot c, b dot a, b dot b, b dot c, c dot a, c dot b, c dot c. Now a dot a, this is a square, b dot b, this is b square, c dot c, this is c square. Now what about this a dot b? If the angle between a and b is gamma, then a dot b equal to b dot a equal to ab cos gamma. And if the angle between b and c is alpha, then b dot c equal to c dot b equal to bc cos alpha. And a dot c and c dot a equal to ac times cos beta. So from this set of things, and if you expand this determinant or simplify, you will get v square equal to a square b square c square times 1 minus cos square alpha minus cos square beta minus cos square gamma plus 2 cos alpha cos beta cos gamma. Now these are the general expression of volume for the lowest symmetry unit cell, that is triclinic cell. Okay, and that will given by a square b square c square into 1 minus cos square alpha cos square beta minus cos square gamma plus 2 cos alpha cos beta cos gamma. So the volume will be a b c root over 1 minus cos alpha minus cos square beta minus cos square gamma plus 2 cos alpha cos beta cos gamma. So these are the volume element in direct space, right? So same thing happens in reciprocal space. In that particular reciprocal space, I have to replace the reciprocal vector ABC by reciprocal vector A star B star C star and interaxial angle alpha beta gamma in terms of alpha star, beta star, gamma star, and the formula will be same. So V star equal to A star B star C star root over 1 minus cos square alpha minus cos square beta minus cos square gamma plus 2 cos alpha star cos beta star cos gamma star. Now for a definite crystal system, if you choose a monoclinic cell, so A not equal to B not equal to C and alpha equal to, so A not equal to B not equal to C, and there must be a definite value of alpha, beta and gamma. If beta equal to pi by 2, then you put beta here in place of cos beta, you put just here beta equal to pi by 2, and you will get a relation where any two term will become 0. So this term and this term becomes 0. For orthorhombic system, what you will get, this alpha beta gamma will be pi by 2, so this terms becomes 0 and we'll get just ABC. Okay, so in this way you can get the volume element of different cell. Now if you just multiply V with its reciprocal lattice volume. So direct lattice volume V and reciprocal lattice volume V star. What you will get? You will get AX, AY, AZ, BX, BY, BZ here, 6 EY, CZ multiplied by A star, AX star, EY star, AZ star, BX star, BY star, BZ star, CX star, CY star, CZ star. And remember the relation among this. They are A star equal to 1. So diagonal elements are 1 and other cross terms are 0. So from that particular thing, if we'll just replace the whole thing here, what you will get? You will get V dot V star is just the dot product between A dot A star, A dot B star, A dot sister, B dot A star, B dot B star, B dot sister, C dot A star, C dot B star, C dot sister. And what you do? You just replace the values of these terms from here in this determinant. So what you will get? You will get that the diagonal elements of this determinant will become 1 and the off-diagonal element all other becomes 0. So its value will be equal to 1. Definite. So how could you transform? So the here you say that the volume of a direct space lattice just inverse to that of volume in reciprocal space, right? So now how could you transform the direct lattice to its reciprocal lattice? You can use the formula just I mentioned in reciprocal lattice. Just I am going to some previous slide. Here. So you can definitely choose these three formula to get this reciprocal lattice vector, and also you remember that A dot A star equal to 1. These are the formula. A dot A star equal to 1. Now if replace A star by B cross C by A dot B cross C, this will be 1. Definitely there will be no problem. So this A dot B cross C is the volume element in direct space, right? So as this is the volume element in direct space, so and A dot A star equal to 1, so I can say that A dot B cross C by V, that will be 1. So from this particular thing I can say that A star will be equal to 1 divided by V divided by B cross C. If you simplify that term, that will be B cross C by V. And from this relation B dot B equal to 1, I can similarly propose that B dot C cross A by V, that will be 1. So here this B star will be C cross A by V, and C dot sister, this will be 1. So C dot A cross B by V, this will be 1. So sister will be A cross B by V. So as you see here, you can transfer from a definite set of vectors A, B, C to the reciprocal vector A star, B star, sister. The same thing happens when you are going to calculate the corresponding direct lattice once you know about the reciprocal lattice. So you can transform from direct lattice to reciprocal lattice. In the similar way, if reciprocal lattice is given for a crystal system, you can transfer from reciprocal lattice to its corresponding direct lattice, right? So with this I am going to end the class 4. So thank you.